Welcome to EduAmp. This is a A-level physics lesson about refraction, part 2, to go with another video. And I'm going to go through how the refractive index is linked to ratio speeds and wavelength. We're going to start looking at an equation for refraction at a boundary of n1 sine I is n2 sine R, and explain why a prism disperses white light. I probably have to make this video in 2 halves. So last week, we were looking at light waves coming along like this, and we saw how they bend towards normal, and I showed you a simulation how you can see wavefronts going through like this and then change direction. Here was the angle of incidence, angle of refraction, and remember the waves were slowed down here first, which made them change direction. So it doesn't make sense, and I didn't mention this before, that the refraction is going to be linked to the ratio of the speeds because it slows down. So there is a diagram on page 190 in your book. Now this diagram is related to, I'm going to move that a little bit there, it's related to this picture just here. Here you can see the wavefronts, and I'm very keen looking at the wavefront here and going to here as it goes into the substance. So here you've gone the wrong way, it's going to have your air, and there's going to be your glass. So the wavefront is here, and it's changing direction. So first of all, this is going to be your normal line, and therefore this is going to be your ray of incidence coming in, and here's going to be your angle of incidence. Now if you look at that, does not make sense then that in fact if you take the wavefront, which is perpendicular to this line going in, here is going to be your angle of incidence. As well as the light goes in, the wavefront changes direction. Therefore now this bit here is going to be your angle of refraction because the light ray comes in here, and then therefore you have your angle of refraction just there. That's where this angle I and angle R comes from. And I remove this now to create a bit more space for me. Therefore, what they've got through is got wavefront X and Y, and when it goes into the glass block, it's going to be X dash, Y dash. Now, the equation you done ages ago, you know speed equals distance, which is S divided by time. Therefore, S, get my little pad to work, S is then going to equal to VT. Ooh, vanished again. Okay, now this distance I was looking at this distance here from Y to Y dash. Therefore, you then know your distance. It's not playing up. The distance going through here. This is going to be your Y dash. Then it will equal CT, because C is going to be the speed of the wave, in this case air, which will be more or less the same speed as through a vacuum. And that's why we're using the symbol C. Conversely, when it goes into the glass block, you now got X dash, which is over here. And what they've done in your book then is they've called that CST, which is then going to be the speed multiplied by your distance. It's CS because that's the speed of light in that substance. So what they got, there's two equations then. That distance there is going to be CT, and that distance there is going to be CST. That's going to be smaller because the light has slowed down, or the waves are slowed down. Now what you got then is a right angled triangle here. We all know from trigonometry that sine I equals the opposite over the hypotenuse. So there's going to be an opposite over here, which is going to be CT. Your hypotenuse is going to be this point here to that point there, which is then going to be your XY. Oh dear, didn't do that very well. It's going to be your XY dash. That means then, by rearranging this equation here, is the CT is then equal to sine I XY dash. Oh, can't fit my dash in, just there. Which means here, taking this equation now, is I can then write down on this one, is on here, and I'll probably go down here, is now your sine R, which is just going to be your angle of refraction here, is going to be the opposite, which is CST, divided by the hypotenuse, and it's going to be a common hypotenuse, which is going to be XY dash. So taking these two equations, you can probably see where it's going now. What I want to do is I want to take this one, also I've got to rearrange that one yet, CS now, t is equal to sine r x y dash. Is I'm now going to take my CT and I'm going to divide it by CST. Well, why am I doing that? Well, I'm doing that because now look at the ratio of the speeds. I've already got the CT here is then equal to sine I, and that's sine I x y dash. And then underneath my CST is going to be my sine R, and that's going to be xy dash. Now we're all getting very excited and we can see what's happening, can't we? The t's are going to cancel. Won't the xy's cancel? And suddenly C over CS is now equal to sine I over your sine R. And I know sine I divided by sine R is going to be a refractive index, hence C equals C over CS. That is where that equation comes from. N equals C over CS. And that means the refractive index is the ratio of the speed of the light in the air compared to the ratio of the speed of the light in that substance. Therefore, what they got in your book, here's got your C sine I over sine R equals C over CS, and then you've got your NS equals C over CS. And that's going to be a refractive index for that substance, glass, whatever you've got. Now, then, and this sort of things I can ask in multiple choice, state what happens to the frequency of light as it refracts. Well, you know the equation, the wave equation, C equals F lambda. Now, as the light goes through from air to glass, what's going to happen is it's going to slow down. Therefore, the frequency, well, say the speed, can go up or it can go down. Well, it's got to keep the frequency the same. And the reason why is with light, we did this earlier in the year, E equals HF, where E is going to be the energy of your photon. H, remember, is your Planck's constant. This remains constant because the energy of the photon must remain constant. It can't change. Therefore, if that goes down, the wavelength goes down. And what it does, it keeps the frequency the same. If the speed goes up, the wavelength goes up. So the frequency doesn't change at all. And what they started then is actually ask you to work out the speed of light in different substance. Well, it's dead easy. All you use is your N equals your C over CS. So case in terms here, when you got glass, I know N equals 1.5. And we all know the speed of light in a vacuum or in air is going to be 3 times 10 to the power 8. And there's going to be the speed of light in that substance. CS equals 3 times 10 to the power 8 divided by 1.5, which then equals 2 times 10 to the power 8, not forgetting our units, meters per second. Okay, I'm probably going to stop it there because the next part of the video is going to all be bringing about this equation here. I know you're all excited, looking forward to part 2. Okay, this is the second part, which I'm probably call it refraction part 4, but it's second part to 13.2 in your book. So, one thing I forgot to mention here was when this equation pops down just about here, when we had the N equals C over CS in your book, you've also got the equation which makes perfect sense where you've got your N. Oh, now I lost my pen. The N is equal to lambda over lambda S. Therefore, isn't going to be the ratio of the wavelength as well, and it's all to do with the fact that this equation here is C equals F lambda. If C goes down, lambda goes down in the same amount. So that's where that equation, that one comes from. Now, this proof here is not too bad at all. Now, this diagram is not bob on which in your book, but I'm going to use it. So what you've got here is I'm going to call that the angle of incidence. There's your normal line. And therefore, here's going to be your angle of refraction just here. Now, this can be any substance, whatever it is, and it's got refractive index of N1. Now, what I mean by that, that's a refractive index as like air into that substance. So this could be water, it could be whatever it is. And this one is going to be glass, and that's a refractive index of that substance. Therefore, when the light travels through there, it's going to have a speed of C1. And when light goes through this one here, it's going to be a speed of C2. Okay. Now, with that then, I know is the refractive index of going from medium 1 going to medium 2, okay, where you're going to have your sine I over your sine R. And that was a terrible R, wasn't it? Try to make it better. And that's refractive index going from 1 going to 2. And sometimes what we do is you write down n and do 1 to 2 equals, because I'm going from 1 to 2. But I know from the previous work we've done, that obviously then equals C1 over C2. Well, I'm going to now use this equation here. Now, it then makes sense, there's a bit of fiddling around, if I can then take 1 over C1, therefore I'm bringing the C1 down here, then that's going to be sine I. Then take that up there, isn't that going to be 1 over C2, and that's going to be sine R. And all I've done is taken that one over there and that one over here. Then I'm going to simply multiply all the way through by C. C over C1 equals sine I equals C over C2 sine R. Now, why have I done that? Well, the bits I'm interested in here, as I'm interested in that one just there and that one just there, because that's the refractive index from that substance, because it's going from air into that substance, and that comes from the equation before was N equal to C over CS, which is actually the same C over C1. Therefore, the final part of the equation pops out here. It's a very, very useful equation. I'll make sure I write exactly the same way in the book. Yeah, I'm going to do it. Is that one is going to be N1, refractive index of that substance. Sine I is then equal to that one, which is N2 sine R. You'll find it in your formula sheet, but this is, and don't worry whether they've written it down here, it's a different notation. That is an absolutely critical equation. Absolutely critical, because that's the one you use all the way through refractive index. And it's going to one you can never use is going to be that one there. And basically that cracks 90% of all refraction questions. So this is the sort of things they can ask you. Now, I'm not going to bother with this part here. These you'll find in summary questions, and they're on the next page or so. Yeah, they're on page 192. And this bit we've done already is about working out the speeds going through, but the bit I'm interested in, this bit here, is you've got, first of all, in this question here, is you've got light travels from a boundary from water into glass. So here's going to be your normal. Missed that there now, and there's the light coming in like this. It's going to then refract towards the, like that one here, going through. And what it's doing now is I'm going from water and I'm going to glass, and because the refractive index is bigger, the glass is going to bend towards the normal, because here you've got the water is given as 1.33 and the glass is going to be 1.52. Greater refractive index, therefore it bends towards normal. So you've got the angle I here and your angle R just there. As I show, the angle of refraction, which is down here, is 46 degrees. So you go into N1 sine I equals N2 sine R. And therefore N1 is going to be your water, 1.33. You then put in your sine I, and the angle of instance, in this case of here, is 55 degrees. Then you've got your N2, which is going to be 1.52. Sometimes they quote it 1.5, but hey, they're going to 1.52 here. And then you've got your sine R just over there. Now, rearrange the equation then, if you start plugging it away through, is I then know my sine R is going to equal to 1.33 multiplied by sine 55 degrees divided all by 1.52. Now, if you bung that in your calculator, you get the sine I equals 0.72. If you then inverse sine that, you'll find then the angle R pops out to 45.8 degrees. Looking at significant figures, we've got 2, therefore won't then R equal what they said is 46 degrees. And that's how you use that equation. Again, use the principles, formula working, answer units.